John, do you want to share your screen?
Sure, sounds great.
Yeah, sorry for the delay.
Let's see. Right.
Let's have no break and let's get started.
Okay.
Okay, so it is really my pleasure to introduce our next speaker, Professor John Wright. So John is an associate professor in electrical engineering at Columbia University. So John has done many great works on low-dimensional models, so including robust face recognition, sparse representations, robust PCA, and John has done pioneering work on geometric analysis for non-convex optimization, which has inspired many of my recent works. So recently, John has interest in deep learning, and today he will talk about the deep learning works and the multiple manifold problems, which is exactly the theme of this workshop. So with this, John, so this is yours. Thanks.
Okay, wonderful. So thank you for the very kind introduction. Thank you to the organizers for organizing this really wonderful workshop. It's been a great collection of talks so far. What I'm going to give today is very much a workshop talk. This is the first time that I've spoken on this subject. So, this is in some sense work in progress and a talk in progress. But I think the theme, as Jacot said, is very aligned with the theme of the workshop. It's really trying to understand how deep networks compute with a particular form of low-dimensional structure and looking for end-to-end guarantees of performance. So like, is it possible to understand resource requirements depth with training in terms of the structure of the data and prove that in some sense you do the right thing? So as I said, this is a very new topic for me. I'm very fortunate to have been dragged into this topic by two fantastic graduate students, Sam Buchanan and Dar Gilboa. Dar is now graduated. But Sam and Dar sort of got me into deep learning. And then as some interesting questions started to emerge, they did some really heroic technical work. So, if you go and download their paper, you'll see what I mean. They did a tremendous amount of heavy lifting to be able to say some analytical things about some of the problems that we're discussing. So most of the credit for this work really goes to them. So deep learning. So as my students and life and the field sort of dragged me into this area of deep learning, I've found myself repeatedly asking everyone around me, what are the model problems in this area? What are the models? Is there a Bohr atom of deep learning? Is there a binary symmetric channel of deep learning, right? Where are the simple models that I can think about? And I feel like for a lot of us, this is a fairly natural impulse, both for reasons of training and reasons of aesthetics, but also because in other applied mathematical fields, we've really seen the power of getting a community of people focused on the right model problems. So this is an example from the area of compressed sensing and sparse approximation, where over the course of several decades, we saw just this amazing flourishing. The bounds got sharper and sharper. The algorithms got faster. People discovered all kinds of different types of low-dimensional structure. And this was all driven by these core model problems of how I reconstruct various forms of low-dimensional stuff from unreliable measurements, incomplete, erroneous, etc. And one of the things that was especially cool about this development is that not only were people getting better bounds or better algorithms, but along the way, there were some, I think, important qualitative insights that came across. And one very basic one that is the theme of this workshop is the role of structure, right? That if we want to think about resource requirements, then we really need to pay attention to the structure of the data. Complementary to that is the importance of isometry. And we saw this in the last talk, right? That we need to make sure that we're preserving the structure of the data. So these are themes that we'll see throughout the talk that I'm about to give. A third theme that comes across at a technical level that maybe is not a top level bullet point, but if you dig into the proofs, One recurring theme that you see is the theme of searching for certificates of optimality. You want to prove that you get the right answer? Well, you find a way, usually via Lagrange duality, of cooking up a certificate that says that that is so. Okay, so this is a very biased sample of some of the insights that have accrued by studying this model problem of recovering low-dimensional structure from unreliable measurements. These and other insights you can hear resonating throughout many of the talks in this workshop. And so it's really natural, if you've just sat through that experience, to ask yourself, well, what are the model problems for deep learning? And at least for myself, after sitting with this question for a while, I sort of came to the conclusion that deep learning is driven by formal model problems, but those model problems are largely defined in terms of data sets, right? They're not mathematical models. Rather, I fix a universe which abstracts some properties of a collection of engineering problems into CFAR10 or ImageNet. And then within that universe, just like in the theory world, we try to get, we might try to get better bounds. Here within that universe, we try to get better performance. And this approach has also been tremendously impactful. I don't think that anyone can deny either the accrual of improved performance or the insights that have accrued. And I think that's, again, kind of a cool thing about this is that, although we may not have a complete mathematical understanding, it really feels like we're learning things, whether it's the importance of depth, right? We saw some of that in the last talk, whether it's the importance of isometry, either by critical initialization or by different approaches in optimization, batch normalization. Some of these interesting phenomena around overparameterization and the role of width. It really feels like we're learning quite a bit at a qualitative level. And so that's great. On the other hand, you might ask then, well, do we really need mathematics in this area? And presumably for most of us on this call, the answer is yes, absolutely. And probably all of you have better reasoned justifications or apologetics for that than I do. But for myself, I come back to a couple of core issues that are hard to address using data alone. And one big issue is the issue of trying to achieve uniform performance, right? I'm in an image classification task. I want to make sure that I'm going to do well for any translation of my input. I want to make sure that a 2-pixel translation doesn't break my system. Well, then I want a for all guarantee, right? I want a for all guarantee, then I need to reason analytically. So that one, to me at least, is fairly clear. Also, maybe a little bit more subtle or a little bit less clear, but I think also pertinent, is the issue of how the role of data structure, right? In this world of data sets, it's actually a little bit hard to get at how the structure of the data influence the solution to the problem, how it influences the architecture of the network, depth, width, and other choices, simply because here the whole world is a single data set, right? It's hard to study these things systematically. And then finally, also, if you want to talk about issues of robustness, it's hard to imagine thinking about robustness without thinking about data structure. And so, despite this tremendous success that has accrued, largely independent of theory and largely independent of mathematical analysis, it still feels like the kind of thinking that we see in this workshop has a really, really important role to play. And so the question that kind of got us started on this work is just trying to understand, well, what are good model problems for thinking mathematically about deep networks? And of course, there's nothing unique in asking this question or in giving this preface to the talk. There are plenty of other answers in the community which are very well justified and maybe even better than the one that you're going to see over the next few minutes. What I'd like to show you is kind of our personal take on this. And this is motivated from two directions. One is from some of the goals that I described earlier, trying to understand roles of low-dimensional structure and looking for some sort of uniform guarantee for computing with nuisances in data, right? Again, making sure that it doesn't break if we rotate the image. And then the other motivation for this is some applied experience, both in engineering and computer vision and in the sciences. And so the specific type of low-dimensional structure, the specific model problem that I'd like to really hammer on for this talk is one of low-dimensional manifold structure. So I have data that live in a high-dimensional space, and I'm going to assume that they lie on low-dimensional manifolds. One canonical source of manifold structure is invariant vision, right? So if I can see my object from any different viewpoint, then the collection of images that I can make cuts out a subset of the high dimensional image space whose dimensionality is the dimension of the transformation group, right? So maybe that's the affine group with 6 degrees of freedom or the rigid body motions or something like this. So naturally, when I think about invariant vision and when I think about looking for guarantees for invariant vision, I'm left with this question of how do we compute with low dimensional structure? Now, the Q&A for the last talk raised a lot of really good questions, and it was a great talk overall. I think to this question in the Q&A of how do we model the structure of natural images, I think that maybe one perspective, just a personal perspective, is that there are some things in the statistical structure of natural images that we will never be able to model analytically, right? Like the distribution of all shapes of chairs, this we need to learn from data. But there's low-hanging fruit here for mathematical analysis. There are some things that we know are going to happen in every computer vision problem, right? Images move, objects move. And so, if we want a starting point, I personally would argue that trying to make sure that we do a really good job of taking care of these structural effects that we know are going to be present is probably a good place to start out. Okay, so invariant vision is one source of low-dimensional manifold structure. Another source of low-dimensional manifold structure is problems in the sciences. So I just picked one particular one. This is from collaboration with Zabi and Zusamarca at Columbia. They're gravitational wave astronomers. So they're interested in these kind of large astrophysical events, like what happens when two really big objects bang into each other. Usually these objects are black holes or neutron stars. And so these are really, really massive objects. And what happens is that as they come close to each other, there's this sort of mutual gravitational interaction that causes them to spiral faster and faster until there's a bang. I was about to say a big bang, but obviously that's not technically correct. Until they merge. And because these things are so massive, they actually warp the fabric of space-time. They create little ripples in space and time that if you build an enormous interferometer, you can actually measure experimentally. And so what you measure is at right of the slide here is this kind of chirp-like signals where the properties of the chirp are dictated by the properties of the astrophysical system. And these are things like the masses of the two black holes, maybe something called a spin. So they're like relatively few parameters that dictate the structure of one of these systems. For each such system, you get a different waveform. And then your problem is, given one of these waveforms embedded in a tremendous amount of noise, number one, can you decide whether there's something present? And number two, can you figure out what it is, either what type of object or maybe estimate the parameters? And so if you think about it, just by virtue of being a system with a few degrees of freedom, this thing has low dimensional structure. In particular, if I parameterize these systems by the masses of the two black holes, well, that's 2 degrees of freedom. I'm going to get some sort of two-dimensional manifold. You can see that visualized at lower right in the slide. It's maybe not a perfect visualization of things, but you can see this kind of strong low dimensional structure in the set of all signals that you can generate. And so just like vision, we started out with some sort of a detection or classification problem, but pretty quickly, just by virtue of this being a physical system and physical systems being simple, we're left with this question of how do we compute with low dimensional structure? And in particular, here the structure is manifold structure. Okay, so in the technical work that I'm going to tell you about today, we sort of made a cartoon of these couple different application areas. And we looked at something that we've taken to calling the multiple manifold problem. Maybe there are other multiple manifold problems associated with other types of learning, but this is the name we're using so far. In this problem, I'm given data that lie on two low dimensional submanifolds. So I have an M plus and an M minus. So I'm given a finite collection of samples, and my goal is to correctly label each of the points on each of the manifolds. Okay, so that's the high level setting. It's pretty simple to state, right? I have two manifolds. I have finite data set, and my goal is to put a positive number on M plus and put a negative number on M minus. So as a goal, I like this because this is very simple to state, right? If you buy that low dimensional structure is relevant to some of these applications, well, this is a pretty clear model problem with a notion of low dimensional structure and a kind of clear criterion for success or failure, right? Either you've labeled the two manifolds correctly or you haven't. And if you do, then you succeed. Now, I'll say, if you like the language of machine learning, then you can think of this as a kind of strong form of generalization in a very restricted problem. Strong form of generalization in the sense that we're putting a probabilistic model on the data, and then we're asking that from your finite sample, you correctly label every point on M plus and M minus. Restricted in the sense that, obviously here we're dealing with a simple structural model. So some of these questions like, what is the distribution of natural images don't really show up here, right? This is just dealing with some of the physical and geometric structure. Okay, but this is the problem that we've been thinking about for a few years. Now, it's pretty clear that the ease or difficulty of this problem depends on the geometry of the data, right? In particular, if the manifolds are higher dimensional, then that's harder. Intuitively, you might believe that if the manifolds are quite curvy, then that's harder. In particular, in our arguments, there's a particular notion of extrinsic curvature that sort of captures how the manifold is curving in the ambient space. Bigger curvature is more challenging. And then obviously, because we're trying to classify data, because we're trying to label two manifolds, the nearness or separation of the manifolds is a parameter as well, right? Closer together, intuitively speaking, is harder, might require more resources. Now, right now is probably a pretty good time for the disclaimer. So we're not going to fully resolve this question in this talk. We are going to show how in some situations we can give end-to-end analyses of neural network training problems that show up here. We can prove that we can correctly label the manifolds. But as you'll see, pretty much every technical result that I'm going to show you, with maybe one exception, has something bad about it. So I'll show you what the one exception is. I'll also try to note the things that are bad as we go. But that's just a disclaimer that although Sam and Dar have done a tremendous amount of technical work around these issues that we'll sort of see as we go, There's still a lot that we don't understand. Okay, but in any case, this is more or less what we would like to do. We would like to, given data that lie on manifolds, correctly labeled as manifolds. Okay, and we're, because eventually we're interested not just in getting a guarantee for that problem, which is probably not the most difficult thing, but we're interested in understanding how neural networks compute with low dimensional structure. We're going to try to do this for a neural network. And the particular network architecture that we're going to look at is a fully connected neural network. Kind of like the last talk, we're going to use some of these ideas about short training time. And like the last talk, there's going to be a notion of isometry that runs through everything. Now, a difference here is that under the hood, the notion of isometry is sort of isometry on the data, right? Like that's the thing that we want to preserve. We want to uniformly preserve the geometry of the data. But some of the tools and ways of thinking that you would leverage to do that are very similar. In particular, as Boris did a great job of explaining, if you're going to randomly initialize your network, you want to make sure that it's critically initialized so that information propagates without things blowing up or contracting. Okay, so we're sort of taking that setting. Now, what are the resources that we have in this problem, right? So our challenges are the sort of geometric structure of the problem, dimension, curvature, separation. Our resources are the data and the architecture. And in particular, the architecture that we're studying is a potentially deep neural network, right? We're going to make it as deep as it needs to be to solve the problem. So L, the depth, is a resource. Also, as Boris did a nice job of describing, the width is a resource. And here, for simplicity, my network is going to have constant width. So we start with some input data dimension, we pop it out to a width n, and then the network is a tube up to the output. So constant width little n. And these are our three main resources: depth L, width little n, amount of training data big N. And then the sort of stylistic theory question is just, well, how should those resources depend on the geometry in order to achieve the goal? Okay, so this is the problem that we would like to study. Okay, now I see there may be a comment or question in the chat. So Boris has a question. Sure, please.
Yeah, can I just ask,
Yeah, absolutely.
Like, so just to kind of wrap my mind around what you're saying, you have these two possibly rather gnarly manifolds that you start with.
Yes.
You're like, my intuition is you'll want to embed them in a higher dimensional space that should make things easier to separate somehow. And like I just wonder, if you turned off ReLU for a second and you just did a deep linear network, presumably if N were big enough, you can just do it even, without a nonlinearity. Or at least, if you give me any finite collection of points, I can separate them in high enough to, so I'm just trying to understand, just a little bit more about that. Like, I understand also the manifolds are nonlinear, so maybe I can't do it with linear, I'm not sure. So I just wonder if you have a comment before you go on.
I mean, yeah, so first of all, I think that's a great question. And, thanks for sort of slowing me down and asking. So I think that there are a couple of questions there. One is, do we need a ReLU network? Could we get away with just a linear network? And in my understanding, in general, the answer would be, the answer to that is no, I can't get away with a linear network here, simply because for the linear network, I basically have a structured linear map from the input to the output, right? It's a linear map that happens to factor as a product of things, but it's still a linear map. So if I start with data that happen to not be linearly separable, then unless I'm missing something, it doesn't seem like a linear embedding of the data would do the trick. I I was up very late last night making these slides, so if I'm making some very basic error, feel free to correct me. But
I think you're probably right. That sounds right.
Yeah. I'll say because I think the spirit of the talk, I feel like this is a really, I really like the problem, and I like some aspects of our analysis, but I don't like all aspects of our analysis. So later on, we are going to see some geometries where that idea would work. So we will see some geometries where things are linearly separable. But in general, as we've set things up here, I think you do need the nonlinearity. Good. Other questions? Or Boris, does that sound good?
Yeah, for sure.
Okay.
I guess, okay, if you're asking for questions, I had one more question about these.
Yeah, sure. I mean, since we're sure.
I mean, so separation seems like a relatively weak way of measuring how different the manifolds are. Like they could be well separated almost everywhere, but be close at one point, and that feels very different. So I wonder if you secretly have in mind something other than separation, and you're just saying that to kind of convey the point.
Yeah, so that's also an excellent question. So this is the formulation of the problem that we started with, and it's sort of separation is sort of a nice worst case property. Just put a tube around each of the manifolds and demand that the other one doesn't enter that tube. And if you take a look at the paper, you'll see that we struggled quite a bit to simply to wrap our heads around this problem. Our paper may not be of book structure, but it's also kind of book length. But I think it's a great question. And so in the work that I'm going to talk about today, so I'll talk a little bit about some approaches to getting guarantees for these problems that work in some simple geometries. In what I'm going to talk about today, you don't get that kind of sharper notion that you're after, but I actually, there is a sharper notion that sort of comes through if you do a sharper analysis. This is not in the paper, but what matters is what ends up mattering, at least as far as I can tell, and this may not end up being canonical, but at least it's the way that I found of thinking about the problem, is if I have manifold 1, it's okay if manifold 2 is close to it at a lot of points. What becomes problematic is if manifold 2 keeps looping back near the same point many times. Is like how many times I loop back. That creates a kind of complicated local geometry, and it seems like the resource requirements, at least in the ways of doing analysis that we know, the resource requirements go up quite a bit when you have that kind of high, I want to call it winding number, but it's not formally a winding number, but like recurrence number, how many times you come back into the neighborhood. Does that make sense? I think your broad point is great. Yeah, clearly these are sort of coarse cartoonish quantities, and so what you're going, anything that you get out of them is going to be loose in general, and sort of understanding what the sharper geometric quantities are is interesting. Sound good?
I didn't mean it as a criticism. I was just
yeah, no, and sorry, I don't mean to sound defensive, because actually it's exactly the right question. I'm just sort of it's good, and actually that's sort of what we're thinking about every day these days. Okay, cool. So maybe I can try to move forward a little bit. So if we want to understand this sort of broad theory question, then we're immediately plunged into the kind of questions that were discussed in the previous talk, right? How do we understand dynamics of training? Because eventually the question is, can we learn a classifier that correctly labels the manifolds? Okay, and so in our paper, we have a particular formulation. This is just minimizing the squared error on the training data. Maybe the notation obfuscates it a bit, but here mu(n) is just the observed data measure, and so this is just minimizing the square loss. And the optimization question in this setting is, does gradient descent correctly label the manifolds, right? Do we find a solution that puts a positive number on m plus and a negative number on m minus? Okay, and so one approach to thinking about these kinds of questions that I personally really like, and that seems to get some traction in simpler problems than this one, is, kind of like we saw in some of the talks yesterday, to think about the geometry and parameter space. And it turns out that a lot of the optimization problems that we can understand in sort of signal processing and machine learning have a particular kind of non-convexity associated with them, which is largely dictated by the symmetries of the problem. Like if you have a matrix factorization problem, then depending on your assumptions on the factors, either you have a permutation symmetry in the middle or you have an orthogonal symmetry in the middle. And if you know what the symmetries are, then you have a pretty nice head start on understanding the geometry. And you can, in some cases, say things about what's going on. This is very hard to do for deep networks. And unfortunately, it seems like the problem that we're confronted with here really asks us for a deep network. We'll see why in a few slides. So, because we're stuck with this model problem, we're kind of stuck with deep networks. And so doing the analysis in parameter space is a little bit of a non-starter, at least with the tools that we have. That kind of compound symmetry is just something that we don't know how to reason about in general. Okay, so what we did for this work is basically to follow what a lot of smart folks in this area of theory of deep learning have been doing. And that's to not think about things in the parameter space where it's complicated, but to try to think in terms of the input-output space. And in particular, then the object that arises very naturally, either by thinking in terms of input-output relationships, or maybe by thinking about short training times, linearizing at initialization, is the so-called neural tangent kernel. We saw a bunch about this in the last talk. Here it is on the slide. You can sort of view this thing in a couple of different ways, but one way of seeing it is that if you fix the size of the two partial derivatives, then this inner product is in some sense measuring the ease of independently adjusting the network output on point X and point X prime. So when X and X prime are distinct, if this thing is small, then the network outputs are, in some sense, less coupled together. And so with a smaller move in the parameter space, I can independently change the outputs at X and at X prime. Okay, so this is the object that's kind of at the center of our analysis. And what Sam and Dar managed to come up with is an approach to reasoning about dynamics using the neural tangent kernel that first of all gives some sufficient conditions for correct labeling of the manifold, and second of all can be sort of specialized to prove that for certain geometries you do correctly label the manifolds. And those conditions are phrased in terms of what we like to call certificates. This notion of a certificate, we'll try to make it clear a little bit later why this is exactly the right thing. But at a high level, what this certificate says is that the fitting error at initialization is close to the stable range of the neural tangent kernel at initialization. Or more precisely, so here the certificate is G. If I can find a small G such that when I push it through theta, I get the effect that I'm trying to undo. I get the fitting error, then I'm in good shape. And under those conditions, so if you have a certificate, it's possible to prove that, yes, indeed, you solve the problem. And in particular, your constant stepping gradient method with an appropriate step size, with an appropriate number of steps, is going to correctly label every point on each of the two manifolds. And, you know, kind of like the previous talk, we're interested in aiming at resource requirements that are realistic. I think a really nice long-term goal is understanding optimal resource requirements in terms of the data structure. Here, what this theorem manages to do is to say that, okay, if you set your depth polynomial in the curvature, the logarithm of the ambient dimension, and some other parameters that I can talk about if you really want. And then you set your network width commensurate with the depth and the number of samples commensurate with the depth. Then indeed, with high probability, both in the random sampling of the data and in the random initialization of the network, you correctly label the manifolds. So this by itself is not a performance guarantee. This is a reduction, right? It says that, okay, if your error is close to the stable range of the NTK in this particular sense, then you're going to succeed. Question? Okay, yes, question, please.
So I have a question, John.
Yeah, great.
I am at lost here
Sure.
about the following, which is quite fundamental. So I apologize, I'm so lost.
No, it's gotta be the presentation. Go on.
In this setting, it really looks like regression or classification. It just looks like a map. There is nothing in this definition and theorem that tells me about manifold 1 and manifold 2. And so it's very hard to appreciate how the manifold structure enters the picture.
Good. Yeah, okay. So, yeah, I apologize. Actually, all of that is the deficit of the presentation. So you're absolutely right to ask the question. So a couple of things. So let's go back to our geometric problem parameters. So we have dimension D, we have curvature kappa, and we have separation delta. Okay, and I mentioned that all of our results, save one of the intermediate lemmas, are bad in some regard, right? Like they're all of them have something that's not ideal. So this result, as stated, is for manifolds of dimension 1. And I'm sorry, it's just the fact that I'm giving this talk for the first time. I really wasn't trying to sweep that under the rug. But these are for manifolds of dimension 1, so that's the dimension parameter. The curvature kappa is entering here on in the requirement on the depth. And you'll notice that there's no separation yet here. So the separation is actually showing up in the certificate, because what the certificate is saying is that my fitting error can be represented as neural tangent kernel on a small function. So if you imagine, we'll see pictures of this later, but if you imagine a situation where the neural tangent kernel, the network is relatively shallow, and so the neural tangent kernel is relatively wide. Then the network outputs on the two manifolds are pretty closely coupled, And you're going to need a very high energy G. You're going to need something that like spikes over here and then goes down over here. You're going to need a very high energy G in order to represent the approximation error. Conversely, as the network gets deeper, as we sort of saw in Boris's talk, there's a sharpening tendency. And this sharpening tendency gives you a better approximation resource, allows you to better independently change the outputs on the two manifolds. And as a result, construct this certificate of small norm. And here I've been vague about what small is, but small should be about 1 over n.
But just for the sake of clarity, in the definition of the certificate, what it is now from the next slides, I'm learning that theta is the neural tangent kernel. I don't know what is G, and I don't know whether M is the ambient space or manifold 1 or manifold 2.
Okay. Sure. Yeah. No, I appreciate the clarification. So here, theta is the neural tangent kernel. This M is the union of the two manifolds. So I'm looking for a function on my pair of manifolds such that if I push it through the neural tangent kernel, I well approximate the fitting error at initialization. And so G is that thing that I'm going to construct. So this first result that I'm describing, aside from deficiencies in the presentation, the reason that it's a little bit confusing is that this first result is kind of a conditional result. It says that if you can find this G, if you can well represent your fitting error in the stable range of the neural tangent kernel, then with high probability, training will proceed and will give you what you want. It will correctly label the manifolds, assuming that you have appropriate resources. So, you know, in some sense, this is less of a theorem than a lemma, right? You can almost see this as like the first lemma in your compressed sensing paper that says that if I have a dual certificate, then I compute the right answer. And here the certificate is this G, which is sort of telling you that the fitting error lives within the stable range of the neural tangent kernel. If I wanted to be sneaky about that, I could just say, assume that the fitting error has small RKHS norm, and just sort of put that into the conditions. But I'm trying to be overt because we want to get that condition out. In particular, what we want to do then is to say, okay, under what geometric conditions does this certificate exist? Because Renee, I think you ask absolutely the right question. This is really going to depend on the geometry of the data, and in particular on dimension separation, curvature. And so, you know, now this is where probably this is good for a workshop talk, but you know, maybe we still have a little bit to do. So we can do this end to end for a very dumb geometry, which is two circles on the sphere. In this two circles geometry, then we get an end-to-end result. Here, the data density can be arbitrary, but the manifolds are restricted. This is a linearly separable geometry. So for this geometry, Boris's question is absolutely enforced. Here you could use a linear network or even a hyperplane. But you know, the maybe interesting thing about this result is that you get an end-to-end result for training a deep network. you can argue in terms of some properties of the data. In particular, now the separation comes in here. The depth needs to be inversely proportional to the separation. You can argue that this certificate exists, and hence that training correctly labels the manifolds. And I'll say that this is where, like, this is where I'd like to sort of fully acknowledge this as a limitation of the work, and also say that we're working on another one. And in particular, it seems like this approach to dynamics via certificates is a good way not just to think about this kind of silly oversimplified geometry, but also to think about other more complex geometries. And so we have work in preparation that does this for more general classes of curves, still for dimension 1, but going beyond this kind of simple geometry, and also beyond the sort of linearly separable geometry. So I guess I would say a couple of things. One is I apologize for the lack of clarity, and I'm going to check back in a second to see how we're doing in terms of getting the message across. 2 is that I think actually, so Dar and Sam did some pretty heroic technical work to be able to prove this. This is actually not very easy analysis, and to get a result that is sort of fully polynomial in all of the parameters is non-trivial. The main weakness of the paper is this this simple geometry, and for that we're trying to get you another one as soon as possible that addresses this limitation. Renee, how are we doing in terms of answering the question? Are there other questions that came up during all of that? Maybe it's sort of too much to respond concisely to.
If you go back to the result, I think I'm very clear now. But
good.
If I had to reinterpret and come up with the simplest possible watered down version of what's written here, in the case of, let's say, even linear classifiers, or even if I put a kernel, right? The G is really kind of the separating hyperplane, and the simplest watered down version of this is that if a separating hyperplane exists, then it perfectly classifies the data. Except that here it's a lot more complex, on the one hand because you've got the kernel, on the other hand because you've got to ensure that's
an interesting interpretation. I like it, but I'm not entirely sure I agree with it.
But the certificate, right? If the kernel was the identity and you make it discrete points, you're just saying the dot product needs to approximate the error. The integral square being small would be kind of the regularization on the linear classifier, like the norm of W typically. That's more or less what it's saying.
Yeah, I suppose so. I mean, that's an interesting interpretation. The way I had been thinking of it, but maybe I sort of thought myself into a very complicated circle. The way I had been thinking of it is twofold. One is in showing that the error has sort of small norm in the norm space that's defined by the kernel. Another is showing that the error lives near the stable range of the kernel. And the latter is sort of the working day-to-day way of thinking about this, that if you're trying to analyze dynamics of training, the stable range of the kernel is sort of where you can cheaply make big changes. And so I can kind of see this as saying that the error is not too aligned with the eigenvectors of the kernel that correspond to small eigenvalues. which are sort of usually high frequencies. But Renee, I agree that what we have on the left-hand side here is not exactly the label, but it's the label translated by the initial network. So, you know, it's something kind of like the label. And now you're saying that this G pushed through the theta reproduces that error. So reproduces something like the label. So yeah, I think I more or less agree with that interpretation. And I think that maybe a way of thinking about this is that this is a notion of separability that's sort of relevant to analyzing the dynamics of training of the deep network. So if you have this particular separability in the kernel that's defined by the network, then training succeeds. So yeah, I like that. I probably have to go back and think a little bit more to decide if I completely
Can I make a comment
think about the subtleties. But I appreciate that interpretation.
So I think I have a way of potentially reformulating what Renee said to make it exactly what he said.
Okay, cool.
And it's kind of nice because it takes your problem and it gives a different version of the same problem.
Okay.
Well, you take the feature vector associated to the NTK, and you use the feature vector to embed your two manifolds into the infinite dimensional RKHS. Now you're trying to separate these two manifolds in a bigger space, but you're only allowed to separate them by a linear separating hyperplane, which is given by this G. I think that's actually the exact same problem. So I mean, of course, formally little d went to infinity, but then something very special hopefully happened because you're aligned with the spectrum of the kernel, and you're functioning in low dimensional space, that the kernel knows about by having this kind of small certificate, roughly speaking.
Right. Yeah, I see. So the interpretation. So if we're going with that interpretation, then the interpretation is that this problem becomes linearly separable when we embed it in the space defined by the kernel.
Yeah, precisely. Like, if you had like two quadratic things, I was thinking about my earlier comment about linear networks. You can't linearly separate them. Well, unless of course you embed using x comma x squared. And then they are linearly separable in that higher dimensional space. And so, now you've used all the power, all the eigenfunctions on the sphere. And so, so now you win because everything is separable because you have all the frequencies or something like that.
Right. And then there's sort of a natural follow-on question, which you're probably too nice to ask, which is, then if that's the case, do you need an analysis of dynamics of training, right? And I think that the answer is actually still yes. Not because you need an analysis of dynamics of training to have a method that provably classifies the two manifolds, but because eventually you'd like to answer some of the kinds of questions that you were alluding to in your talk, which are, what happens at longer training times? How does feature learning proceed? What's special about a deep network in terms of adapting to the geometry of the data? If this is an image manifold, how does a convolutional network take advantage of that? And so I sort of, I think it's a good point, and I really appreciate both Renee's question and your sort of precise reformulation of this. And I think it's still interesting to talk about dynamics of training and sort of have end-to-end guarantees for training neural networks in this setting, even though I think, as you sort of implicitly pointed out, there may be relatively simple methods that correctly classify the manifolds. I mean, you would still have to work out how much data you need and things like this, but you imagine that you could get the bounds.
No. I want to be clear. I think it is interesting to understand the
Cool.
learning.
Yeah, no, I was more like doing that for myself and also sort of rhetorically for the room.
Yeah. No, I mean, your point that you need the large depth is exactly to align the spectrum of the NTK with the kind of, you know, frequency at which the difference lies. That's what you're saying. But then when
Exactly.
the NTK, you know, when the NTK is sharp like that, you might be a little worried it changes too much, that this, you know, the training is not stable. I mean, your network is pretty deep. So it's like there's something non-trivial to be like calculated there. It's got to be deep, but not too deep, you know?
Yeah, yeah. And I think this sort of resonates with your, with your talk, is that eventually you're going to need width that depends on the depth, because as you get deeper, those sort of statistical fluctuations become more significant.
Yeah, precisely right.
Yeah, okay. Very good. So I think my talk started like 20 minutes late, and now it's almost getting towards the end, but I think I'm going to try to say just a few more things about what's going on here, maybe just convey a few intuitions. So, you know, one is, as we described earlier, so if we talk about resources and resource trade-offs in this problem, so here, depth is an approximation resource, right? As the network becomes deeper, the NTK becomes sharper. It becomes better at fitting functions with high frequency content. And so you want a depth that is commensurate with your geometry, but maybe ideally no deeper than that. So this is the first resource. Depth is an approximation resource. Kind of as we saw in Boris's talk, the network width is a statistical resource. So if you have a shallow network, then this thing doesn't concentrate very sharply about this. Sorry, if you have a narrow network, this thing doesn't concentrate very sharply about this limiting form, but as the network becomes wider, it concentrates. And under the hood here, if you're interested in these sorts of things, one of the technical pieces in this analysis that is somewhat sharp is the analysis of this concentration. So kind of like we saw in the last talk, the key phenomenon here that makes it possible to do analysis at all is that you have a sequential structure on the problem. So you start with an input, you hit it with some independent randomness that gives you your next features, hit it with some independent randomness, next features, hit it with some independent randomness, next features, and so on and so forth. And so it turns out that tools from martingale concentration are extraordinarily well adapted to handling this kind of sequential randomness. And that sort of makes sense, right? For those of you who are not so familiar, martingales sort of have their origin in studying Gambler's Ruin and, you know, what happens if you make a sequence of bets. At what point do you run out of money, or at what point does your NTK fluctuate too much from its nominal value? And so if you couple those tools with some really careful analysis of how information propagates in a deep network, in particular this kind of deterministic propagation of lengths and angles, then it's possible to sort of combine this to get a result that says that this thing uniformly concentrates about its what is essentially its expectation, its nominal value. So the formula here is sort of what you get if you work out a nominal value for the NTK. This is phrased in terms of some functions phi L that describe how angles propagate through the network. And what you can prove is that if the width is a little bit bigger than the depth, then indeed this thing concentrates uniformly over the two manifolds. And you can make this precise by sort of putting a bound on the largest fluctuation. So in our entire analysis, there are many things that are suboptimal. The sample complexity is suboptimal. The final prescription for the width on the depth is suboptimal because we don't have a great way of handling changes during training. But this is one piece that does seem to be essentially optimal and sort of matches the observed statistics and experiments. And the key to getting that to happen is sort of to use martingale tools and a lot of careful thought about propagation of information through the network. So that's one piece. And then, finally, kind of unsurprisingly, the last resource that shows up in the problem is the amount of sample data. And the sample complexity, and this is sort of to the last comment that you want the network to be as deep as possible, but not too deep. Intuitively speaking, if you want to do well at fitting functions on the two manifolds, then you need a number of samples that sort of commensurate with the aperture, right, with the width of the kernel. So the pipeline is something like the geometry sets the depth. The depth sets both the width of the network, which is one statistical resource, and the number of samples that you need, which is another statistical resource. Okay, and so overall, if you quantify these things, then you get the trade-offs that are described in the theorem here. In particular, in this setting and under these assumptions that we've now discussed in quite a bit of depth, you can have correct labeling of the two manifolds when the depth is set commensurate with the geometry, and when the width and sample complexity are set commensurate with the depth. And again, all of this sort of comes from these basic intuitions about the neural tangent kernel, but making it precise is a pretty hefty technical task. Okay, and so then just to reiterate, since we're getting near time, so there are sort of two parts to the talk. So we set up this kind of simple model problem of two manifold classification. We gave a reduction of the analysis of the geometry of this problem to the existence of a certificate. Renee and Boris helped us to do a better job of interpreting what that certificate might mean in terms of the structure of the problem. And we also alluded to some constructions of certificates for simple geometries. And the constructions that are in the paper sort of go by harmonic analysis. There's this observation that you can think about the kernel and frequency domain. As the network gets deeper, then the decay of the Fourier coefficients gets slower. And so that's a resource that you can leverage to fit functions that change more rapidly. So that's the viewpoint that gives the certificate construction in the paper. The viewpoint that we've been working with in the past few months that seems promising in terms of generalizing beyond these simple geometries doesn't directly do this in Fourier domain, but instead does it in the spatial domain, and is leveraging pretty heavily these decay properties of the kernel. Again, that it's like important that you choose a deep enough network such that your kernel is concentrated as much as possible on a nearby region where things should be labeled together. Okay, so with that, I think I'm pretty close to the end of the talk. It should be pretty obvious that there are a lot of directions for future work here. I like this general theme of trying to link data structure to architecture and trying to prove end-to-end guarantees for classification for deep networks. An obvious direction is to improve the generality of the results. There are some aspects of the proofs that generalize right away to higher dimensional manifolds. The main place where generalization is needed, those in this construction of certificates. Again, they're doing it in time domain instead of frequency domain seems to be, more or less the way to go. Another obvious question is, we motivated this from invariance and invariant vision. So what about convolutional networks? There are some similar issues that arise in the sense that this propagation of information in fully connected networks can tell you things about propagation of information in convolutional networks. Having sharp probabilistic results is kind of challenging because you have a structured probability model. You sort of need to decouple, or it's a little bit hard. I think what's really interesting in the second direction is less the mechanics of proving theorems, but instead really understanding what are the conditions that we need on image manifolds to sort of guarantee good performance for a convolutional network. And then finally, the obvious direction is to get beyond the neural tangent kernel regime. Here I'll say that there are some problems where we do know quite a bit about dynamics of feature learning. These are problems that are much simpler than deep neural networks. As we described before, deep networks have this kind of compound symmetry structure. But for some kind of toy versions or simplified versions of dictionary learning, deconvolution, things like this, we understand pretty well the landscape of optimization and pretty well the dynamics of optimization. And you can sort of see phenomena emerge like from a random initialization, individual features learn, symmetry is broken in particular ways. So, that's not to say that this directly helps at a technical level to solve the problem that we talked about today, but it there are some interesting phenomena there that might be suggestive. Okay. So with that, I'll just close by, again, thanking my collaborators, thanking the organizers for organizing this really nice workshop, and thanking everyone who asked questions or offered comments during the talk. It's fun to have this much back and forth. So thank you all, and happy to take more questions if we have time.
Okay, so thank you, John, for this very wonderful and stimulating talk. We already have very a question, so we have a few more from the chat. Nihai, do you want to ask by yourself?
Okay.
Yes. So, thanks, John. So the question that I have, so you obviously were able, showed us a link basically between the data structure and the architecture. My question is, what do you say basically on all of these recent results, relatively recent results on adversarial attacks, and how they are transferable across our architectures? So basically adversarial attacks, they're going to poison the data, maybe change the structure, but they are transferable across architectures. So in the light of your, theory, how do you explain that?
Okay, well, first of all, that's a great question. So the short answer is that I don't know. But I think it's a good question. Now, the theory that we described today doesn't have any adversarial attacks in it. In fact, it doesn't even have any noise in it. Doing a noisy version of the theory seems relatively routine as far as I can tell, at least for small noise levels. It seems mostly technical. But this question of adversarial attacks is really interesting. And one of the questions that maybe just because I spent time thinking about robustness in computer vision, where you have very specific kinds of things that can go wrong, right? Like somebody shaves their eyebrows or takes off their glasses. And so these are particular structured attacks, or maybe not even attacks. I mean, that's the thing. Like these are just regular phenomena, but they can cause systems to fail. And so there you have you have some physical basis for sort of thinking about the kind of perturbations that you want to be robust to. And for myself, I actually find that a little bit, I find it easier to think about those kinds of questions than about adversarial attacks on neural networks. I mean, adversarial attacks are interesting because maybe they can tell us something about the commonalities of architectures or the ways in which they differ from human perception. It's definitely a worthwhile endeavor. But in terms of trying to defend against them, like, I'm scared that we're not defending against non-adversarial things. And, you know, so whether it's transformations of the domain, whether it's occlusion. And I think it would be really interesting to think about those kinds of questions in a model like the one that I described here. We haven't done anything like it, but you can imagine sort of picking your favorite norm, like an L1 norm for capturing sparse occlusions, and then putting sort of a norm ball around the manifolds, and then running a version of the problem where now you ask to get the right answer on this expanded region. That would be a cool thing to try. I don't have strong intuitions for the resource requirements for doing that. Presumably, you would have to have a pretty structured model for the perturbations, and maybe a sparse model is a good one, or maybe in some other basis. But it's a great question. There might be some interesting direction there, and I like the spirit of your question, because I really feel like it's hard to reason about robustness without some structural model for the outliers, kind of like René's talk. You had a model that some of the points are corrupted, but it's only a fraction of the points, and some model for the inliers. And so, yeah, maybe there's leverage to eventually do something like that here.
Thank you.
Sure, thanks.
So any other question from the audience? Okay, so actually I have one question. So,
Sure.
so from the analysis, so did you try to characterize how the feature looks like? So by feature, I mean like the layer before the output, like so what's the dimensionality of the features look like, and what's the margin or somehow like this?
Yeah, that's good. So I think there are a couple of intuitions that I can convey. So first of all, if you care about what's rigorously in the analysis, what's rigorously in the analysis is for short training times. And the reason that it's easy to analyze, well, I shouldn't say easy, because this was hard, and the last talk was significant technical work as well. Like, these things are hard to analyze, but the reason that we can get started at all is because near initialization, information propagates in a sort of pretty deterministic way. And so for a randomly initialized network, just based on the statistics of the network weights, you can diagnose what mapping is applied to the data, how the data are becoming more correlated. And they do become slightly more correlated as you go through the network, simply because this is a ReLU network, right? And so when you take the non-negative part, then things get more correlated. And so there's like a slow, like 1 over depth contraction. And in the initial feature set, in the initial feature set, you sort of have images of the two manifolds under this contraction, randomly rotated. And then the interesting question, which is sort of the big analytical question in this area, is, well, okay, over time, what happens to those features? And it's sort of clear, if you sit down and think intuitively about the dynamics of training, that if I just think about features at a given layer, the tendency is to try to push the manifolds apart. And so what's hard about reasoning about slightly longer training times is the fact that you're sort of training all of the layers at the same time. And so you need to ensure that the motions between those features are sort of compatible. And it absolutely feels like they are, but coming up with the right sort of couple dynamical system to really nail that is a little bit is a little bit tricky. Another approach to thinking about how features evolve is sort of to move away from convex model problems, right? Because there are some non-convex model problems where I say convex model problems because in the NTK regime, things sort of act convex, but maybe there's leverage in moving to sort of non-convex model problems. And again, there are some non-convex model problems where we actually know a few things. So,
Yeah.
And good?
Yeah, that's good. Yeah. Okay.
Okay.
So you have no more questions. So let's thank John for one more time. And okay, so we will have a short lunch break. And so we will resume at 1 o'clock Eastern time. So we will have roughly 20 minutes for the lunch break. Thank you everyone for joining this work, and thank you for the wonderful speakers.